All right, we're going to get started. Here is an exponentially. How do I look? Okay. Is my light turned on? You should put it over there. No. Okay, lights turned on. We've got to solve for x. Are you ready to solve for x? Okay. We're going to use all of our prior knowledge about logarithms. We've been putting in different characteristics and different properties to help us get us ready for this day right here. The first thing I want you to understand is that we have to isolate the base. Let's put that. Let's verbalize that. We've got to isolate the base before I can solve any equation. What I mean by base is there's the base. So I like to call anything that's not the base a Klingon. There's a 4 there in front, so we have to subtract a 4 from both sides. So subtract a 4, and I get negative e to the 2x is equal to what, 517. There's a negative in front, so we need to get rid of that guy. We need to divide by -1, and I get e to the 2x is equal to negative 517. Okay. And so then this is what we learned, what, 3 days ago? 3 days ago I stood in front of you and said, I've got to be able to change an equation, an exponential form, into a logarithm. So let's do that. This is log base e. So that base is e of negative 517 is equal to 2x. And so we can also write this as the natural log of negative 517 is equal to 2x. And then let's divide by 2. So x is the natural log of negative 517 all over 2. So that's what we're doing today. What do you got? I went ahead and wrote log base e, understanding that it's actually ln. So that's what the natural log is. It's log base. So it's 2 ways of saying the same thing. Is that okay? Now, when you plug this in your calculator, you're going to get no real answer. How come I get no real answer here? You can't take the log of the negative. Now, think about the graph of a log. When we graph a log, we have a vertical asymptote here, and it looks like that. The domain of any log is any x value greater than 0. So it turns out this one is no solution. I can't find a number raised to the 2x power that when I take 4 minus that number equals 521. But the process holds true for any equation like that. Okay, we've got 11 more to go. You ready? Buckle in here. We've got a 45-minute explosion of equations. Here's another one. Sample 2. Do you guys see a Klingon on this equation? There is. There's one Klingon. It's the -5. The base includes the exponent. So this is the base. Right? It doesn't include. It includes the -3, but it doesn't include the -5. So let's add that 5 to both sides. I get 10 to the x minus 3 is equal to 130. That looks like an exponent that I can change to logarithmic form. Let's do that. So this is log base 10. So let's see. There's log base 10 of 130 equals x minus 3. So we're just changing the exponent into logarithmic form. So log base 10 of 130 equals the exponent. Is that okay? And we would talk about if you have trouble converting an exponent to a logarithm, it's going to be tough. We have to add 3 to both sides, so we just do log base 10 of 130 plus 3 equals x. So that's it. A lot of times we will have to get a decimal answer. Let's do that. Let's see, log. I'm getting 5.1. Let's do another one. Questions? Anyone? Yes.
You didn't like add the 3, so is it you have to type it in that way to detect it?
So be careful. I think you got to put a parenthesis around this.
So you got to type in 130.
You got to do log base 10 of 130. Here, let me show you what I did. Did you not get 5.1, Kyle?
No, I just wanted to get it typed in that exact.
Yeah. Let's see here.
Add the 3.
Here's what I typed in. Let's see, what would happen if I typed in log of 130 plus 3? Oh, that's a no-no. That's right. This is taking a log of 133, so you got to close that parenthesis and then add 3 to it. Is that okay?
Yeah.
Another way to make sure you don't mess up is I could do 3 log of 130. Sorry, 3 plus log of 130. And there's the 5 one. Yes. Well, there's a couple ways you can change your base formula. Here, so you want me to show you? So you want to do something like log base 5 of 2. So on mine, I might go to math, and my math menu has a log base feature. So this would be log base. We said log base 5 of 2. So 5 to the 0.43 power is 2. If you don't have that menu, you do the change of base. You do log of 2 divided by log of 2 divided by log of 5. Here, let me just make a point here. So if you don't have that change of base thing, it's called the change of base formula. You take the log of the second number over the log of the first number. So a lot of calculators don't have it, Jennifer. So if I go to math and go down all the way, many calculators don't have this. This is a new feature that olders don't have. You don't have it? Okay. All right, that's equation 2. Here's equation 3. So how is this? This is important. How is this equation different than the other 2 that we just did? I kind of gave you a clue there. Different bases. So log base 10 and log base E are nice because they're in our calculator and they're easy to compute with your calculator. But there's no log base 2 in our calculator. Well, there is some for us, but sometimes there's not. But there is. So let's do. There's a Klingon. There's 7. So we're going to add the 7 to both sides, and we're going to get 2 to 3x equals 12. So that's exponential form. We're going to rewrite it in logarithmic form. So I'm going to throw a log here. This is log base 2 of 12 equals 3x. That should feel natural by now. Hopefully it does. If it doesn't, we need to write this out about 100 times tonight. And you should be able to go from that form to logarithmic form, no problem. We're going to divide by 3. So log base 2 of 12 divided by 3 is x. And that's x. However, sometimes we ask for the decimal form, and so can you execute that? Let's do that on the calculator. Suppose I'm stuck with the calculator without that magic log base feature. So I need log base 2 of 12. That's log of 12 divided by log of 2. So just to show you, if I go to math, and if I go to log base and I do log base 2 of 12, I get the same number. So you should be practicing that on your calculator. Can you actually carry out that computation? And then to get the answer, I still need to divide by 3. So let's divide this by 3, and I get 1.2. X equals 1.2. Approximately. What questions do you have? Here, about a fourth of the way through. I told you we're going to do about a dozen of these. We're about a third of the way through class, so we need to keep on moving. Look at this guy. This is where we're going to make our money. This one was different. Why is this one different? What do you got? I'm recording this lesson for anybody. Well, see, you seniors missed this. On senior skip day, this is what I looked like when I made that video. Well, no, it's behind there. It's up there. It's just running. It's going to be a 45-minute video. When I'm watching, I have to fast forward through the boring stuff, which I understand is probably all of it. But. All right, you got that written down? Yes. Julia's gone. Henrik's gone. No, he is here. Julia's. She came up to me and said, "Could you record this?" No, I'm not doing you a favor. If you came up to me and asked me that too, How is this one different? How is this one different? I see 2 different bases here. So the way we handle this is this. I'm going to verbalize our step. We're going to take the log of both sides. And this is a reasonable step. This is valid. I can do that. So it looks like this. It's log of 4 to the 2x minus 3 equals log of 3 to the 5x. It's just like if I add a 5 to both sides, or if I divide by 3, or if I multiply by 2, I can take the log of both sides, and I do not change the equation. I don't change the value of x. So the purpose of this is to use that power rule that we learned yesterday. Now I can take the powers and move them in front. So this becomes 2x minus 3 times the log of 4. This becomes 5x times the log of 3. Let me try to, so sometimes people, right, this goes in front. So that's the whole purpose of the log, is it changed that exponent into a multiplication. And now we can use our algebra 2 rules. I've still got to get x by itself, so let's distribute the log. So anything with an x in it, I'll move to one side. Anything without an x, I'll put to the other side. So let's see. So this looks confusing. I hope yesterday that card game, remember the card game? Chris was the champion. You understood that logs are just numbers. Log 3, log 4, those are just numbers. And so basically it's just getting x by itself still. I got to take an x out. So let's take an x out of this. And now look at that, I got x. I can divide both sides by that parentheses, and I'll have the answer. So x is 3 log of 4 divided by 2 log of 4 minus 5 log of 3. That's a doozy. It's not even 4. When you type this in your calculator, you're going to want to make sure you do parentheses around the second, around the denominator, just to make sure that you're dividing by that. It seems like this got a little bit harder, didn't it? Not more difficult? You're going to want to try that on your own sometime. There's one on your homework. Did you see your whole homework list over there? I should have given that to you a week ago. There it is. Are you ready for the next one? We've still got 8 more equations to go. So how is this one different than what we just did? Does it have Klingon? Cindy, can you not see that? There we go. This is the first equation with a log in. Okay, the other ones are exponential equations, so these are logarithmic equations. They have a log in them, and so we're going to have to go the opposite direction. Shane, what are you taking a picture of? Oh, yeah. Because you're catching someone doing something they shouldn't do.
No.
What's that? I don't know. I was looking. Maybe someone was sleeping or doing some Spanish or something. All right, I'm stalling here so you can write this down. Does this one have Klingons? It does, right? It has the -10 and the 3. So we have to, instead of isolating the base, we have to isolate the log. So the log is everything included in the parentheses. So that's what we have to get by itself. We'll just add a 10, divide by 3. So this is log base 5 of x minus 3 is, so that's going to be 20. So 30 over 3 is 10. All right. Now we got to go the other way down the street. I've got to change that log into an exponent. So it's on that first day we talked about how do we change, and you did that worksheet. You sat there and changed 1,000 of these. The base is 5, the exponent is 10, and it's equal to x minus 3. So 5 to the 10 is x minus 3. So then x is 5 to the 10 plus 3, which is a pretty large number. That's all right. You're about halfway there. It's kind of like drinking from a fire hydrant, huh? Another one. So how is this one different than any one we've seen? There's no, very good. There's no Klingons here. Yes. Woo. No Klingons. And so that's going to happen. Most of the time, they're going to try to throw a Klingon you got to get rid of. But I'm ready to jump in exponential form. Let's just go ahead and do it. We can do it because there's no Klingon. So the base is 3. The power is 2. 3 to the second is the x squared minus 8x. So if you're still looking at me, how in the world, what did he just do? That's a problem. All right, you have got to be comfortable changing logs to exponents and vice versa. It's going to be this is like going to be your worst week ever if you haven't figured that out yet. Look what we have. We have a quadratic equation. I'm going to subtract the 9, and this is just your old factorable, good old factor theorem. So x equals 9 and negative 1. Okay, we're about halfway there. Look, that's example 6. I said we're doing 12 today. You're going to have a bunch of examples to look at when you drive through all those. Look at all those equations on 4.5. Oh, this one's already stalled. Let me take that away, and we'll do it again. hey, this one doesn't have a Klingon, but it has 2 logs, so that's an issue. I can't convert 2 logs into a single exponent. So I've got to combine these 2 into 1 log. What we learned yesterday, we have to condense into 1 log. So I'm going to verbalize that. Condense to 1 log. So we learned that when we add them, we multiply. So it's actually log base 5 of those 2 items multiplied together. Can we change to an exponent now? Heck yes, we can. Heck yes. Let's do it. So this is 5 to the first. 5 to the first equals your x plus 3 times x minus 1. That's your quadratic equation again. What do you know? Big surprise there. All right, so this does factor, let's see. This does factor in x plus 4, x minus 2. So x is negative 4 and 2. Does anybody see it? There's a gotcha here. We're about ready to get got. Why can't we have a negative 4? So when we go to check our answers here, and we get log base 5 of, let's see, negative 4 plus 3 is negative 1. I can't take the log of negative 1. Not feasible. In fact, what's the domain of that first function? The domain is going to be x is greater than negative 3, because isn't that a horizontal shift to the left? So if I were to graph that, I'd have a asymptote at negative 3, and I can't plug numbers to the left. So I can't plug numbers left of negative 3, so this is a gotcha. We just wipe it off the board. Now, just because it's negative doesn't mean it's a gotcha. I just showed you an example, and you can have it in your notes. Negative 1 is not a gotcha. Because when I plug negative 1 into this, when I do log base 3 of negative 1 squared minus 8 times negative 1, I can evaluate that, because that's just log base 3 of 1 plus 8, which is 9. And that's a valid log. 3 to the second is 9. So just because it's a negative value doesn't mean it's a gotcha. You've got to plug it in and see if it actually is a valid solution. Okay. A lot of kids will think, oh, it's negative, so it's not good. But that's just not the case. Okay. How about this one? Let's take that guy away. Do this one again. I can't change 2 logs in an exponent, so I have to condense this just like the previous one. So let's condense this using the subtraction rule. This is log base 5, and I will be dividing x plus 1 over x minus 1 equals 2. So condensing. Subtraction turns into division. Let's change that to an exponent now. The base is 5. The power is 2. 5 to the second. In fact, I wonder if I can just do this. So 5 to the second equals x plus 1 over x minus 1. So we're not left with quadratic. What type of equation are we left with? Rational. Let's get rid of the denominator by multiplying by x minus 1. So that leaves me with 25x minus 25 is x plus 1. And heck, this is 1b stuff. All right, we get 24x equals 26. So x is 13/12. Still with us, Allie? It might be time to see how you're doing. Let's give you one that you can do on your own. No. Here we go. Do this one. Take about, shouldn't take it too long. I see a couple Klingons there. All right, you should be engaged. You should be trying to figure this one out. I'll do it as well, right here on this green piece of paper. And see if you can't get the decimal approximation when you're all done. Anybody got an answer? I think I got one. Gene, I saw you working. Good. There you go. Taking the day off. All right. I got a negative 0.53. Is that the right answer?
Yeah, that's right.
Let's see. Darren, did you add a 10? You added a 10 and divide by negative 2, and you should get 3.5. Negative, no positive, because you're going to add the 10 and get negative 7, divide by negative 2, and you get 3.5. So that's the first step, is to get those Klingons rid of them. So we added the 10 and got negative 7, divide by negative 2, we got 3.5. So now we're ready to write this as a natural log of the 3.5 equals the 7's v plus 5. And now we have more Klingons. So natural log of 3.5 minus 5 divided by 7. So you gotta be careful how you type that in. You might want to put parentheses there. I typically play it safe on these. And what I mean is that I'll do this. I'll first do the natural log of 3.5 minus 5, get that number, and then divide that by the denominator, so it doesn't get messed up with your order of operations. All right, let's go back to so if they have, remember when we took the log of both sides? We can undo the log of both sides. So if we have the log of this equals the log of that, this is about as easy as it gets. All we do is we drop the logs, and we get x plus 3 equals 2x. So putting in 2 logs on both sides is equivalent to taking it away. And so here we just get 3 equals x, and we're done. So you might be lucky enough to find equations like that. So let's now do an equation that doesn't require a log with the same concept. There's an example of an equation that you have in your notes that looks like this. you tell me what it is? I'll go back to it. So remember this one here, you're way back. Here it is, where we had 4 to the 2x minus 3 equals 3 to the 5x. This is about the hardest one today. This one takes a lot of, you got to be careful and watch your signs. But the one I just put on the board can be done easier. And you can do that technique. You can take the log of both sides. But if I can change them to have the same basis, what I'm saying is, if I can do this, 9 is 3 squared. If they have the same base, then I could just cancel the bases. And so then what I'm going to end up with is 2x equals 2x minus 6. So we're just dropping the exponents, much like we drop the logs. Same idea. When I subtract 2x, I'll get 0 equals negative 6, and then I'll get no solution. This equation has no answer. Let's do another one like that. Let's do 1/6 to the power of x minus 3 equals 36 to the power of x. Let's just go 3x. So you can kind of smell the same situation. We have two numbers that can be written with the same base, much like 3 and 9 can be written with the same base. You could not do that with this problem here, because 4 and 3 cannot be written with the same base. But if they're going to give it to you, then use this technique. 1/6 is 6 to the negative 1. And then 36 is 6 squared. I like putting parentheses around the x minus 3 because you have to distribute that minus 1. The 6's go away, and I'm left with just the exponent. Negative 1, x minus 3, has to be 6x. So negative x plus 3 equals 6x. How do you mean? Oh, yeah, you can do that. All right, let's do one more thing. These, look at these guys. These look troublesome. I'm already telling you what they are. These are quadratics incognito. We're going to be using our quadratic techniques to solve these. The U substitution thing, remember that? That's what's going to happen. So on this first one, I'm going to let u equal e to the x. It's always that first guy right there. So that will allow me to express, if I square u, then that'll be e to the x squared, which will be e to the 2x. So it turns out e to the 2x is a quadratic form of an equation. So let's replace these two ideas. We get 3u squared minus 5u plus 2 is 0. We're going to mark this if we have to. But since 3 and 2 are prime, there's nothing wrong with just doing trial and error. Let's see, I'm going to need a 2 here and a 1 there with a minus and a plus. Think that'll work? No, that doesn't work. This negative times a positive is not a minus. Minus and minus. This, oh, what is that?
Pardon the interruption.
Good morning.
Can I have Kyle Brewster stop by the attendant's office after this block, please?
Sure can.
Thank you.
All right, here's the factor form. The factor theorem, the zero product property says that u will equal what? 2/3 and u equals 1, if I set each one equal to 0 and isolate u. But let's solve for x. So instead of u equaling 2/3, I have e to the x equaling 2/3, and then I have e to the x equaling 1. So instead of u equaling 2/3, I've got to go back and replace that e to the x for u. So now I've got to solve those equations with a natural log. So this becomes the natural log of 2/3 is x, and this becomes the natural log of 1 equals x. That's it. I'd probably leave it like that unless they ask for the decimal forms. That's tough, isn't it? Do you have a question on that?
Please pardon the interruption. This is a reminder that announcements will begin in 1 minute. Thank you.
You should be able to do most of this homework. I'm going to post this on D2L. We'll start tomorrow. We'll start where we left off. But we did get through 92% of it today.